Somewhere out in the dark, there is a star so large that if you placed it where our sun sits, its glowing surface would swallow the ground beneath your feet, then Mars, then Jupiter, and reach all the way out to the orbit of Saturn. Light itself, the fastest thing in existence, would need nearly 3 hours just to crawl from one edge of it to the other. This is why the story of Stephenson 218 is not really a story about a single star at all. It is a story about the outer limits of what matter is even allowed to do before physics itself begins to break. About a monster hiding inside an ordinary-looking smudge of light, and about a question that sounds simple until you try to answer it. How big can something get before the universe says no more? Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath and let's begin. You are sitting somewhere right now, and everything around you feels solid. The chair holds your weight. The walls stay where they are. The floor does not move. And because of this, your mind has quietly built an entire idea of what large means, stitched together from the biggest things you have ever stood next to. A mountain feels enormous because you have to tilt your head back to see the top of it. An ocean feels endless because you cannot see the far shore. A city feels vast because it takes an hour to drive from one side to the other. These are the yardsticks your brain reaches for, and every one of them belongs to the surface of a single small planet. They are the right size for a human life, and they are almost useless for what we are about to look at, because the thing we are traveling toward does not belong to the world of mountains and oceans. It belongs to a scale where the words we normally use simply stop meaning anything. So before we go anywhere, we have to fix the ruler we are using. Start with the ground under you. Earth is a ball of rock about 12,700 kilometers across. That number already sounds large, and in human terms, it is. You could fly for an entire day and still not cross the whole thing. Now hold that ball in your mind and set it next to our star. The Sun is roughly 1,390,000 kilometers across. That means you could line up about 109 Earths in a single row and still not quite bridge the face of the Sun. And if you wanted to fill the Sun completely, you would need something like 1,300,000 Earths poured inside it. Already the mind starts to slip. You can picture one Earth. Maybe you can picture 10. But somewhere past a few dozen, the number stops being a picture and becomes just a word. A big-sounding word that your brain files away without ever truly seeing. Hold on to that feeling, because we are only at the very first step. The Sun, this thing that dominates our entire sky, this furnace that pours out enough light to warm a planet from 150 million kilometers away, is about to become a speck. Our star pours out an astonishing amount of energy every single second. Deep in its core, where the pressure is beyond anything you could ever build, hydrogen is being crushed into helium at a rate of hundreds of millions of tons each second. A sliver of that mass vanishes and turns into pure light and heat. And that sliver is what lights our days and grows our food and keeps the oceans from freezing solid. The Sun has been doing this for around 4.5 billion years, and it has enough fuel to keep doing it for roughly another 5 billion. By every measure that matters to us, it is the most important object in existence. And by the measure of the cosmos, it is small, ordinary, and forgettable. Astronomers file our Sun under a modest little label. They call it a yellow dwarf. The most powerful thing you will ever see with your own eyes. And the universe has already decided it belongs in the category of small things. To understand why, you have to understand that stars are not all built the same way, and they do not all live the same kind of life. A star is a balancing act, and it is one of the most delicate balancing acts in nature. On one side, gravity is pulling everything inward, trying to crush the entire star down into a single point. Every scrap of gas is being pressed toward the center by the weight of everything above it. On the other side, the fusion burning in the core is pushing outward, a constant storm of energy fighting to blow the star apart. For most of a star's life, these two forces sit in a near-perfect standoff. Gravity pulls in, radiation pushes out, and the star holds its shape, steady and bright, for millions or billions of years. The size a star settles into depends almost entirely on one thing: how much material it was born with. A star that forms from a small amount of gas ends up small, cool, and dim, sipping its fuel so slowly that it can burn for trillions of years. A star that forms from a vast amount of gas ends up enormous, blazingly hot, and desperately hungry, burning through its fuel so fast that it lives and dies in just a few million years. More mass means more gravity. More gravity means more crushing pressure at the core. More pressure means faster fusion, a hotter fire, and a shorter, more violent life. The biggest, brightest stars are not the old wise elders of the galaxy. They are the ones that burn hardest and vanish soonest. But here is where the story turns strange, and where the word large begins to fracture into two completely different meanings. When we ask which star is the largest, we could be asking two very different questions, and they do not have the same answer. One question is about mass. How much stuff is packed into the star? How many tons of gas? How much raw material sitting in one place? The other question is about size, the actual physical width of the star, how far it stretches from one side to the other. You might assume these are the same thing. The heaviest star should be the widest star, surely. But the universe does not work that way, and the gap between those two ideas is exactly where our monster lives. The most massive stars we know of are not the widest. They are ferociously heavy, tens or even hundreds of times the mass of our sun, but they hold themselves in a relatively compact ball because their gravity is so overwhelming that it refuses to let them spread out too far. They are like a heavyweight fighter, dense and powerful and coiled tight. The widest stars are something else entirely. They are not necessarily the heaviest. Instead, they are stars that have swollen up, ballooning outward to sizes that seem impossible. Their outer layers puffed so thin and so far from the core that they barely hold together at all. These are the giants of physical size, and they are what happens when a star reaches the end of its life and begins to fall apart in slow motion. Our own sun will one day become one of these swollen giants, though a modest one, billions of years from now, when the hydrogen in its core finally runs low. The balance that has held it steady for so long will start to fail. The core will contract and heat up, the fusion will spread into the layers around it, and the outer envelope of the sun will begin to expand. It will swell outward, growing dozens and then hundreds of times wider than it is today. It will redden and cool at the surface, even as its core burns hotter than ever. The sun will become a red giant, and as it does, it will reach out and consume the innermost planets, and it will scorch the Earth into a lifeless cinder long before it ever touches us. That is the fate of an average star. Now imagine that same process, but starting with a star born vastly larger than the sun. Imagine the swelling, the reddening, the ballooning outward, but applied to a star that was already a giant to begin with. That is what we are traveling toward. Not just a red giant, but a red supergiant, one of the largest single objects that the universe is capable of assembling. To find our monster, you have to look toward the constellation of Scutum, the shield, a faint patch of the southern summer sky that most people have never heard of and could not point to. It is not a bright, famous constellation. It has no dazzling stars that catch your eye on a clear night, but it sits along the plane of the Milky Way, in the direction of one of the richest, most crowded regions of our galaxy. And buried in that direction, thousands of light years from Earth, hides a cluster of stars called Stephenson 218. For a long time, this cluster was barely noticed. It is far away, and it is hidden. Between us and it lie enormous clouds of gas and dust, the raw material of the galaxy, and that dust does something cruel to starlight. It absorbs it. It scatters it. It reddens and dims everything behind it, like fog swallowing the glow of distant headlights. So for years, the true nature of what lived inside that cluster was smeared and muffled, its light strangled on the long journey to our telescopes. It took the arrival of instruments that could see in infrared light, the kind of light that slips through dust where ordinary visible light cannot, to finally pull back the veil. And when astronomers looked into Stephenson 218 with those infrared eyes, they found something that stopped them cold. There, embedded in the cluster, was a red supergiant, so vast that it challenged the very upper limit of how big a star is thought to be able to grow. Let us try to put a number on it, though you should know in advance that the number is going to fail you. Numbers always fail at this scale. The best estimates place the radius of Stephenson 218 at somewhere around 2,150 times the radius of our Sun. Sit with that for a moment. 2,150 suns, laid end to end, just to span the distance from the center of this star to its edge. Its full width, then, is more than 4,000 times the width of the Sun. Remember what we said earlier. That light needs about 4.5 seconds to cross the face of our Sun. Light, the fastest thing in existence, moving at just under 300,000 kilometers every second, needs 4.5 seconds to travel from one side of our star to the other. To cross Stephenson 218, that same beam of light would need nearly 3 hours. Think about what that means. You could sit through an entire afternoon, hour after hour, and light would still be traveling, still crossing the face of a single star. Nearly 3 hours for light to make a journey. It completes across the Sun in the time it takes you to say a short sentence. Let us try another way in, because the light comparison is almost too abstract to feel. Picture our solar system. At the center sits the Sun. Around it, the planets trace their wide, patient orbits. Mercury, closest and fastest, whips around in just 88 days. Then Venus, then Earth, then Mars, all of them rocky worlds circling in the warm inner region. Beyond Mars lies a vast gap, and then the giants begin. Jupiter, the king of the planets, orbits at around 780 million kilometers from the Sun. Then Saturn, even farther out, with its rings, drifting at roughly 1.5 billion kilometers. Now here is the part that breaks the mind. If you took Stephenson 218 and dropped it into the exact place where our Sun sits, its glowing surface would not stop at Mercury. It would not stop at Venus, or Earth, or Mars. It would swallow all of them, easily, without even noticing. It would engulf the asteroid belt. It would swallow Jupiter whole. And it would reach outward, its blazing edge extending all the way to the orbit of Saturn, the ringed planet. Everything you think of as the inner solar system, every world we have ever set foot on, or sent a lander to, or dreamed of colonizing, would be buried deep inside this single star, drowned in its outer layers like pebbles at the bottom of an ocean. If you were somehow standing on Saturn, as this star took the Sun's place, you would not see a star in your sky. You would see a wall of glowing gas rising up and filling the entire heavens. A surface so close and so vast that the concept of a star would no longer make any sense. You would be inside it. This is the scale we are dealing with. And yet, here is the twist that makes red supergiants so strange, so counterintuitive that it took astronomers a long time to fully accept it. For all its unimaginable size, Stephenson 218 does not contain nearly as much material as you might expect. Its mass, the actual amount of stuff inside it, is thought to be only around 20 times the mass of our Sun. Perhaps a little less, since a star like this sheds material constantly. 20 times the Sun's mass, spread across a volume so enormous that it could hold billions upon billions of suns. Do the arithmetic in your imagination, and you arrive at something almost absurd. This star is, on average, thinner than air, far thinner. The outer layers of a red supergiant are so wispy, so diffuse, that they are closer to a vacuum than to anything you would call a gas. If you could scoop up a handful of the star's outer envelope, you would find almost nothing in your hand. The material is stretched so thin across such a gigantic volume that the average density of the whole star is a tiny fraction of the density of the air you are breathing right now. The monster is, in a sense, mostly empty. It is a vast, glowing cloud held loosely together, a furnace at the center, wrapped in an envelope so tenuous that the edge of the star is not even a real, sharp boundary. There is no surface you could stand on. There is only a gradual thinning, the gas growing fainter and fainter until it simply fades into the surrounding space. Where exactly does the star end? The honest answer is that it does not end anywhere in particular. It just trails off. This is one of the reasons measuring a star like this is so fiendishly difficult, and why the numbers come wrapped in uncertainty. You cannot lay a ruler against something that has no clear edge. So how do astronomers even begin to measure a star they cannot travel to, cannot touch, and cannot even see with ordinary light through the dust? The answer is a kind of detective work, a chain of reasoning that turns faint smudges of light into hard numbers. It starts with distance, because without distance, nothing else can be pinned down. A dim star that is nearby and a brilliant star that is far away can look exactly the same from Earth. Brightness alone tells you nothing until you know how far the light has traveled to reach you. For Stephenson 218, the distance comes from the cluster it belongs to. Because it sits among a group of stars that were all born together from the same cloud, astronomers can study the whole cluster and work out roughly how far away the entire family lies. The current estimates place it at something like 19,000 light-years from Earth. That distance alone should give you pause. The light entering a telescope from this star tonight left it around 19,000 years ago. When that light began its journey, the last ice age still gripped our planet. There were no cities, no writing, no farms. Our ancestors were hunters moving across a colder, wilder world, and they would not build the first permanent settlements for thousands of years. All that time, this beam of light has been racing across the galaxy, threading through gas and dust, only to arrive now, in our lifetime, to be caught and measured. Once the distance is known, the true brightness can be worked out. If you know how far away a light is, and you know how bright it appears, you can calculate how much light it is actually pouring out. And Stephenson 218 pours out an ocean of light. Its total energy output is thought to be on the order of hundreds of thousands of times that of our Sun. Every second, it radiates more light than our star will produce in days. But almost all of that light is not the kind your eyes could see. Because the surface of a red supergiant is relatively cool, at least as stars go, much of its energy comes out as infrared light, as heat rather than visible glow. Its surface temperature is only around 3,000 degrees. far cooler than the roughly 5,500 degrees at the surface of our Sun. This is the strange bargain of the red supergiant. It is cool and red at the surface, yet staggeringly luminous overall, and it manages this precisely because it is so enormous. A cooler surface gives off less light for every patch of area. But when you have a surface this unimaginably vast, all those dim patches add up to a torrent of energy. Brightness, temperature, and size are locked together in a simple relationship. And once you know two of them, the third falls out of the equation. Astronomers measure the temperature from the color and character of the light. They measure the brightness from the distance and how bright it appears. And from those two, the size emerges, that jaw-dropping radius of around 2,000 suns. This is how you weigh and measure a giant you can never visit. Not with a tape measure, but with light, distance, and the unbending laws of physics. But there is a catch, and it is an important one. Every number in this story comes with a shadow of doubt hanging over it. When you hear that Stephenson 218 has a radius of around 2,150 suns, you should not picture that as a precise, settled fact carved in stone. You should picture it as the best estimate we can make, surrounded by a fog of uncertainty. The dust that hides the star also distorts our measurements of it. The distance to the cluster is itself only known approximately, and if the true distance is different, then the true size shifts with it. The fuzzy, edgeless nature of the star means that different methods of measuring can disagree. And red supergiants are not steady, calm objects. They pulse, they shudder. Their outer layers heave in and out over months and years, so the star is not even a fixed size from one measurement to the next. It swells and shrinks like a slow, cosmic breathing. This is why you will sometimes hear different stars named as the largest ever found. There is a whole short list of these titans, and their rankings shuffle as measurements improve. There is UY Scuti, which for years held the popular title of the largest known star, sitting not far from Stephenson 218 in the same crowded region of the sky. There is Westerlund 126, another monster contender. There is VY Canis Majoris, a legendary supergiant that has long featured in these conversations. Each of these stars has been measured and remeasured, and each time the numbers wobble, the crown passes from one head to another. Stephenson 218 currently sits at or very near the top of that list. But the honest truth is that the very idea of a single, definite champion is a little bit of an illusion. These stars live so close to the theoretical upper limit of stellar size that they are all clustered together near the ceiling, jostling within the margins of our own uncertainty. What matters is not really which one holds the record by a few percent. What matters is that all of them are pressed up against a wall, a boundary in nature that seems to say, this far and no farther. Because there does appear to be a limit, stars cannot simply grow without end. There is a size beyond which a star cannot hold itself together at all, a threshold where the outward push of the star's own light becomes so fierce that it tears the outer layers away faster than gravity can hold them. A star trying to grow past this point would essentially blow itself apart at the surface, shedding its outer envelope into space in great expanding shells of gas. And this is exactly what we see the largest supergiants doing. They are not stable, placid giants sitting quietly in the dark. They are shedding material constantly, bleeding their own substance into space, surrounded by shells and clouds of gas that they have thrown off in fits and pulses. Stephenson 218 is losing mass at a tremendous rate, wrapped in a cocoon of its own expelled material. The monster is, in a very real sense, coming apart even as we look at it. To understand how a star ends up this way, we have to go back to its birth and follow its whole life, because a red supergiant is not a young star. It is an old one, near the end, and everything about its monstrous size is a symptom of its coming death. Stephenson 218 was not always this vast. It began, as all stars do, inside a cold cloud of gas and dust drifting through the galaxy. Somewhere in that cloud, a region grew denser than its surroundings, and gravity began to pull material together. More gas fell inward, the clump grew, and as it grew, it heated up, squeezed tighter and tighter by its own increasing weight. Eventually, the center became hot and dense enough that fusion ignited, and a new star switched on, blazing into the darkness for the first time. But this star was born greedy. It formed from a large amount of material, and so it came into existence as a massive, brilliant, blue-white star, tens of times heavier than our Sun and thousands of times more luminous. A star like that lives fast. Where our Sun sips its fuel gently over billions of years, a massive star like the one that became Stephenson 218 devours its fuel at a furious pace. It burns so hot and so hard that it exhausts the hydrogen in its core, not in billions of years, but in just a few million. For a star, that is the blink of an eye. And when the hydrogen in the core finally runs out, the careful balance that held the star steady begins to collapse. Without the outward push of core fusion, gravity gains the upper hand. The core contracts and heats up, and this new heat ignites fusion in the shells around the core, and it forces the outer layers of the star to expand. The star swells. Its surface, now spread across a vastly larger area, cools and reddens. The blue-white giant of its youth transforms into a bloated, crimson supergiant, its outer envelope ballooning outward to those staggering sizes we have been describing. This is where we catch Stephenson 218 now, in this swollen, unstable, late stage of its life. Inside its core, a desperate sequence of events is playing out. Having burned through hydrogen, the star moves on to fusing helium, and when the helium runs low, it fuses heavier elements still, carbon, oxygen, and onward. Each stage burns faster than the last, releasing less energy and buying the star less time. It is a losing battle, and the star knows only one way for it to end. Because a star this massive cannot simply fade away quietly the way our Sun eventually will. Its core is building up heavier and heavier elements, layer upon layer, like the rings of an onion, until at last it begins forging iron. And iron is the end of the line. Iron is the one element that gives a star no energy when it fuses. When the core fills with iron, the furnace that has fought against gravity for millions of years finally falls silent. There is nothing left to push back. And in that instant, gravity wins completely. What happens next takes less than a second. The iron core, unable to support itself, collapses inward at a fraction of the speed of light. In the space of a heartbeat, a core larger than our Earth is crushed down into a ball only a few kilometers across. The infalling material slams into this newly formed core and rebounds, and the outer layers of the star, all that vast, swollen envelope, are blasted outward in a titanic explosion. This is a supernova, and for a brief time, a single dying star can shine brighter than an entire galaxy of hundreds of billions of ordinary stars. The elements forged in the star's core and in the fury of the explosion itself are hurled out into space, scattered across the galaxy. The iron in your blood, the calcium in your bones, the oxygen filling your lungs right now, all of it was made inside stars like this one and flung outward when they were torn apart. The atoms that make up your body are the ashes of ancient giants. Stephenson 218 is destined for exactly this fate. sometime in the astronomically near future, though that may still mean many thousands of years from now. This colossal star will reach the end of its fuel and collapse. And when it goes, it will not go gently. Given its enormous mass, it may leave behind one of the strangest objects in the universe. If the collapsing core is heavy enough, no known force can stop its fall. It keeps collapsing, past the point of a dense stellar remnant, past every limit, crushing itself down until it forms a region where gravity is so extreme that not even light can escape. A black hole, the largest star we have ever found, may well end its life by becoming one of the darkest, most inescapable objects that physics allows to exist. From the largest thing to a point of infinite density in the span of a single collapse. There is a poetry to that which is hard to ignore. The very quality that makes Stephenson 218 so extraordinary, its immense mass, is also the thing that seals its violent fate. The bigger the star, the harder it falls. Let us step back from the fate of the star for a moment and return to the sheer, dizzying question of its size, because there is still more to understand about just how alien this scale truly is. We have said that the Sun could hold more than 1 million Earths. Now consider that Stephenson 218 could hold billions of suns inside it. If you tried to fill the volume of this single star with copies of our own, you would need somewhere on the order of 10 billion of them. 10 billion suns, each one already capable of swallowing 1 million Earths, all packed inside the volume of one star. The numbers pile on top of each other until they lose all meaning, and that is exactly the point. There is no experience in a human life that prepares you for this. You have never seen anything even remotely this large. Nobody has. The largest thing you have ever laid eyes on is probably a mountain range, or the curve of the horizon over the sea, and those are features on the surface of a tiny planet that would be an invisible moat inside this star. Try walking around it instead of filling it. Imagine you could travel around the outer edge of Stephenson 218, circling its equator the way you might imagine flying around the Earth. The distance around our planet is about 40,000 kilometers, a journey a fast plane could make in a couple of days. The distance around this star is so vast that even traveling at the speed of light, the fastest anything can move, you would need most of a day to complete a single lap. Nearly 9 hours of unbroken travel at 300,000 kilometers every second, just to circle one star a single time. And through all of that, you would be moving past a surface that is not solid, not still, but churning and pulsing, racked by convection currents larger than entire stars. Great cells of rising and falling gas, each one big enough to swallow our whole solar system. The surface of a red supergiant is not a smooth ball. It is a boiling, heaving, restless thing, blotched with enormous bright and dark regions where hot gas rises and cooler gas sinks. Each blotch, a storm of a size that has no comparison anywhere in ordinary experience. If you could somehow watch it up close and sped up in time, you would see it seething, shuddering, throwing off great streamers and shells of gas into the surrounding darkness. Now compare it, gently, to a few of its rivals, because seeing the family of giants together helps the mind grip the scale. Take VY Canis Majoris, one of the most famous supergiants of all. For a long time it was held up as the ultimate example of a monstrous star, and it truly is a giant, with a radius estimated at well over 1,000 times that of the Sun. If you placed it where the Sun is, it too would engulf the orbits of the inner planets and reach out toward Jupiter. And yet Stephenson 218 is thought to be larger still, reaching farther, out past where even VY Canis Majoris would stop. Take UY Scuti, which many people first learned about as the biggest known star. It sits, like our monster, in the crowded star fields near the Shield constellation. For years it wore the crown. But as measurements were refined, its estimated size settled somewhat, and Stephenson 218 rose above it. The point of all this shuffling is not to crown one final winner. The point is that we have found a whole population of stars pressed against the absolute upper limit of what a star can be. And Stephenson 218 stands among the very greatest of them, perhaps the greatest of all that we currently know. Somewhere out there, in the parts of the galaxy still hidden behind dust, there may be one larger still, waiting to be found. That possibility should thrill you rather than disappoint you. It means the record is not really a record at all, but an ongoing search, and the universe is still keeping some of its largest secrets. There is a question that naturally rises up at this point, and it is worth facing directly. Why do these enormous stars form in this particular corner of the sky? In these crowded clusters near the Shield constellation, along the busy lanes of the Milky Way? The answer has to do with where stars are born and what they are born from. The most massive stars can only form where there is a great deal of raw material gathered together in the dense, rich clouds of gas and dust that pool along the spiral arms and the inner regions of the galaxy. These are the fertile grounds of star formation, the places where the galaxy is actively building new suns in great batches. Stephenson 218 sits in exactly such a region, in a direction that looks toward the inner galaxy, where the density of gas is high and the ingredients for building giants are plentiful. Stars there tend to be born in clusters, dozens or hundreds of them, condensing out of the same vast cloud at roughly the same time. And in a cluster like that, among all those siblings, a few will happen to gather up far more material than the rest, and those few will become the monsters. They will also be the first to die, burning through their lives in a geological instant, while their smaller siblings are only just getting started. So a cluster like Stephenson 218 is a kind of snapshot, frozen at a particular moment in its history. The most massive stars that were born in it are already in their final, swollen supergiant phase, on the very edge of collapse, while lighter stars around them will keep shining calmly for billions of years to come. We are seeing the giants of the cluster in their last act, caught in the brief window before they explode. If we had looked a few million years earlier, they would have been brilliant blue-white stars in their prime. If we look a few million years from now, they will be gone, replaced by neutron stars and black holes and expanding clouds of debris. We happen to be watching at exactly the right moment to see them at their largest. That is a strange kind of luck. Out of the entire lifetime of a star, spanning millions of years, the supergiant phase is a fleeting final chapter. And yet when we point our telescopes toward that cluster, that is precisely the chapter we find written across the sky. It is a reminder that everything we see out there is a moment caught in a much longer story, a single frame pulled from a film that runs for eons. The light we are collecting tonight left the star long ago, and by the time it reached us, the star itself may already have changed in ways we cannot yet see. For all we know, gazing at that light, 19,000 years old, the monster may already have died, and we are simply watching a ghost, an image of a giant that lived and burned and perhaps already exploded, its final light not yet arrived at Earth. We cannot know until that news reaches us, crawling across the galaxy at the speed of light, thousands of years in the sending. Let us return to that idea of the limit, the ceiling that all these giants seem to press against, because it points to something deep about how the universe is built. Why should there be a maximum size for a star at all? Why can a star not simply keep gathering material and growing forever, becoming ever larger without end? The reason lies in the war between gravity and light that we described earlier, and in a particular way that wore tips at the extreme end. As a star grows more massive, it also grows vastly more luminous, and it does so out of all proportion. Double a star's mass, and its light output does not merely double. It leaps upward many times over. So the most massive stars are pouring out truly ferocious amounts of light, and that light carries a pressure, a physical push against the material of the star itself. At a certain point, this outward push of radiation becomes so strong that it overwhelms gravity's grip on the star's outer layers. The light is literally blowing the surface of the star away, driving powerful winds of gas outward into space, stripping the star of its own substance. A star that tries to grow beyond this threshold cannot hold onto the extra material. It sheds it as fast as it accumulates it. This is the limit, the ceiling, the reason there are no stars 100 times wider than Stephenson, 218, wandering the galaxy. Nature has drawn a line, and it enforces it with the star's own light. The giants we find are the ones that grew right up to that line and are now paying the price for it. Hemorrhaging material, unstable, throwing off shells of gas as they teeter at the very edge of what a star is permitted to be. And there is one more layer to this, a subtlety that makes the biggest stars even harder to build. The very first stars that ever formed in the universe, long ago when everything was young, were made almost entirely of the simplest ingredients, hydrogen and helium, with almost none of the heavier elements that stars like our Sun contain today. Those primordial stars may have been able to grow even more massive than anything we see now, because the physics of pristine gas allowed larger objects to form and hold together. Over billions of years, as generation after generation of stars lived and died, they enriched the galaxy with heavier elements, and that enrichment subtly changed the rules. Modern stars, built from this enriched material, feel the push of radiation more strongly, and so they tend to cap out at somewhat lower masses than the giants of the early universe might have reached. In a sense, Stephenson 218 is about as large as a star can be, given the era of the universe we live in and the material available to build it. It is a champion of its time, pressed against the ceiling that our particular moment in cosmic history allows. Imagine, for a moment, that you could stand on a world orbiting Stephenson 218, if such a world could even exist. The truth is that it almost certainly could not, at least not in any way that would let you stand there and look up. Any planet that had formed close to this star would long ago have been engulfed as the star swelled into a supergiant, swallowed the way our own inner planets will one day be swallowed by the dying sun. And any planet far enough out to survive would be so distant that the star, for all its size, would still be a strange sight, a vast but cool red presence hanging in a dark sky. But let us indulge the impossible and imagine standing at the distance of, say, Saturn's orbit, with the star filling the place of the sun. You would not feel warmth on your skin the way you feel our sun's heat, or not in the same way, because so much of this star's energy pours out as infrared, as invisible heat rather than visible light. Above you would hang an enormous, deep red disk, dull and vast, filling a huge swath of the sky. It would not blaze with the fierce white brilliance of our sun. It would glow like an ember the size of the heavens, a smoldering red wall stretching from horizon to horizon. There would be no sharp edge to it, no clean circle. Its boundary would be soft and fuzzy, fading into the dark, and it would seem to shimmer and pulse if you watched it long enough, breathing in that slow, supergiant rhythm. It would be one of the most awe-inspiring and terrifying sights any conscious being could ever witness, and there is almost certainly no one out there to witness it. That is one of the quiet, humbling truths that runs beneath all of this. These grand cosmic spectacles unfold in the dark, mostly unseen, for billions of years, in silence. The universe does not build its wonders for an audience. Stephenson 218 has been swelling and pulsing and shedding its substance across the galaxy for its entire long life, and until very recently, no eyes had ever seen it, no mind had ever known it existed. It took creatures on a small planet, 19,000 light-years away, building instruments to catch the faint infrared glow leaking through the galaxy's dust, before this monster was ever noticed at all. For the entire history of life on Earth, through the age of the dinosaurs, through the slow rise of our own ancestors, this giant burned unseen and unnamed. And now, in the span of a single human lifetime, we have found it, measured it, and begun to understand it. That is worth pausing on. The same species that once could not explain the sun rising in the morning has now reached across 19,000 light-years of space to weigh a star it will never touch, to measure a giant it can barely see, and to work out its size, its temperature, its life story, and its coming death. We did that with light and mathematics and patience, standing on our tiny world, looking outward. There is something else about these giants that deserves a closer look, and it is the way they refuse to sit still. We tend to imagine stars as fixed points, steady and unchanging, the same tonight as they were 1,000 years ago. For most stars, over a human lifetime, that is roughly true. Our sun changes so slowly that across all of recorded history, it has appeared essentially constant. But red supergiants are different. They are among the most restless, variable stars in the entire sky. Their brightness rises and falls, sometimes over months, sometimes over years, as their bloated outer layers pulse and heave. The star literally changes size, expanding and contracting, growing brighter as it swells and dimmer as it shrinks, in a slow, irregular rhythm that never quite repeats the same way twice. This pulsing is one of the reasons these stars are so hard to measure precisely. When you try to pin down the size of Stephenson 218, you are trying to measure something that is, in a sense, always in motion, never settling on a single fixed radius. The best you can do is capture a range, a band of sizes across which the star breathes. And that breathing is not gentle. The forces involved are colossal, moving quantities of gas that dwarf entire ordinary stars, sloshing that material in and out across distances that light itself takes hours to cross. Sometimes the pulsing grows violent enough to fling great gouts of gas clear off the star entirely, adding to the shroud of expelled material that surrounds it. Over time, a supergiant like this can shed an amount of mass equivalent to many suns blown off into space in these episodes of instability. That lost material does not simply vanish. It drifts outward, cooling, and out in the cold darkness surrounding the star. Some of it condenses into dust, tiny grains of solid matter forged in the outflows of the dying giant. This is one of the great underappreciated roles that supergiants play in the galaxy. They are dust factories. The grains they produce drift out into space and become part of the raw material for the next generation of stars and planets. The dust in the cloud that formed our own solar system, some of the very material that eventually became the rocks of Earth and the atoms in your body, was manufactured in the outflows and death throes of stars like Stephenson 218, long before the sun was born. So there is a deep connection here, threading across billions of years, linking these distant monsters to the ground beneath your feet. The giants live, swell, shed their substance, and die, and in doing so, they seed the galaxy with the ingredients of new worlds. We are, in the most literal sense imaginable, the descendants of stars like this one. Not metaphorically, physically. The iron, the carbon, the oxygen, the calcium, the silicon, all the heavier elements that make up our planet and our bodies, were cooked inside massive stars and scattered by their deaths. When you look at Stephenson 218, you are looking at a factory that builds the very stuff that living things are made from. You are looking, in a way, at a distant ancestor. It is worth spending a little time on the history of how we came to know about stars like this at all, because the discovery of the largest stars is really the story of how our tools grew powerful enough to see them. For almost all of human history, the stars were simply points of light, fixed in the night sky, mysterious and unreachable. Nobody knew what they were made of, how far away they lay, or how large they might be. They were pinpricks in the dark, and the idea that one of them might be so vast it could swallow our entire inner solar system would have seemed like pure fantasy. The first great leap came when people realized that the stars were suns in their own right, other stars like our own, only impossibly far away. That single insight transformed the night sky from a nearby ceiling of lights into a scattering of distant furnaces, each one potentially a sun with its own worlds. But knowing that a star is a distant sun does not tell you how big it is. To measure the size of a star, you first have to know its distance. And measuring the distances to the stars turned out to be one of the hardest problems in all of science. The breakthrough came from a beautifully simple idea. As the Earth travels around the Sun over the course of a year, our viewpoint shifts from one side of our orbit to the other. Nearby stars appear to shift ever so slightly against the background of more distant ones, the same way a nearby object seems to shift when you look at it first with one eye and then the other. By measuring that tiny shift, astronomers could triangulate the distance to the nearer stars. It was painstaking work, requiring instruments of extraordinary precision, because the shifts involved are minuscule. But it worked, and for the first time, humanity had real distances to real stars. Once you have distance, and once you can measure how bright a star appears and what color it is, the door swings open. You can calculate the star's true brightness, its temperature, and from those, its size. The tools kept improving. Better telescopes gathered more light. New techniques let astronomers spread starlight out into its component colors and read the story written there, the temperature, the composition, the motion of the star. And then came the ability to see in wavelengths of light beyond the visible, into the infrared and beyond, which turned out to be essential for finding the largest, coolest, most dust-shrouded giants. Stephenson 218 owes its very discovery to these advances. It is too far, too dim in visible light, too buried in dust to have been recognized as anything special with older tools. Only when astronomers could pierce the dust with infrared eyes did the cluster reveal what it was hiding. The star gets its name from the astronomer who cataloged the cluster and the cluster's number in that catalog, a quiet, technical name for one of the most extraordinary objects ever found. There is a lesson in that, about how the greatest discoveries often arrive wrapped in modest, unglamorous packaging. A catalog entry, a faint smudge, a number that turns out to conceal a giant. Now let us confront the question that quietly nags at anyone who hears these numbers. How can we possibly trust them? How can astronomers claim to know the size of a star 19,000 light-years away, a star they can barely see, buried behind curtains of dust, when they cannot even reach the nearest star to our own sun? It is a fair challenge, and the answer reveals something beautiful about how science actually works. The measurement of a star like Stephenson 218 is not a single act. It is a web of independent lines of evidence, each one imperfect on its own, but together forming a picture that holds up. Astronomers measure the color of the light to find the temperature. They measure how the brightness changes over time to understand the pulsing. They compare the star to other stars of known properties. They model how stars of different masses and ages behave, and check whether the star fits those models. They account for the dust in the way, measuring how much light it absorbs and correcting for it. They estimate the distance through the cluster the star belongs to, cross-checking it against multiple methods. And when all of these threads are pulled together, they converge on a consistent story, a star of a certain temperature, a certain brightness, and therefore a certain size. No single measurement proves the case, but the agreement of many independent measurements, each probing the problem from a different angle, builds confidence. This is why the numbers come with error bars, with ranges of uncertainty rather than single exact figures. Honest science does not pretend to a precision it does not have. When astronomers say Stephenson 218 has a radius of around 2,150 suns, the word around is doing real work. The true figure might be somewhat smaller or somewhat larger. Future measurements, with better instruments and better understanding of the dust and the distance, will sharpen the number, and it may shift. That is not a weakness of the science. It is its strength. The willingness to say, we think it is roughly this large, but we are still refining it, is exactly what separates real understanding from mere assertion. And even with all that uncertainty, the broad conclusion is rock solid. Whatever the exact figure, this is one of the largest stars ever found, a genuine titan pressed against the upper limit of stellar size. The details will be refined for years to come, but the essential truth, that we have found a star large enough to swallow the orbits of the inner planets and reach out toward Jupiter and Saturn, is not in doubt. We really have looked across 19,000 light-years and found a monster. It helps, sometimes, to build the scale up one step at a time, slowly, so that the mind has a chance to climb the ladder rather than being thrown off the top of it all at once. So let us climb it together, carefully. Begin with something you can hold, a grain of sand. Now think of a beach ball. The beach ball is vastly larger than the grain of sand, but you can still hold both in your mind at once, still compare them. Now let the grain of sand be the earth, and let the beach ball be the sun. That is already a jump that stretches the imagination. 109 Earths across the face of the sun, but you can just about hold it, a grain and a ball. Now here is where the ladder gets steep. Take that sun, the beach ball, and shrink it back down until it is itself the size of a single grain of sand. Everything scales down with it. The earth becomes a speck of dust, far too small to see, a mote invisible to the naked eye. And now, at this new scale, where the mighty sun is nothing but a grain of sand, how large is Stephenson 218? It would be a sphere several meters across, a grain of sand beside a great boulder. That is the leap. That is, the gulf between our sun and this star. Our sun, which holds 99.8% of all the mass in our solar system, which could swallow more than 1 million Earths, which dominates our entire sky and our entire existence, is a grain of sand beside a boulder when set against this giant. And remember, even this boulder, this titan, is itself a small thing on the scale of the galaxy. The galaxy contains hundreds of billions of stars, and the vast majority of them are far smaller than the sun. Tiny red dwarfs, sipping their fuel in the dark. Stephenson 218 is a rare monster, one of a handful of true giants scattered through a galaxy of hundreds of billions. If you could see the whole galaxy laid out, these largest stars would be the rarest of jewels. A few dozen genuine titans among an ocean of ordinary and dim stars. And the galaxy itself is one of hundreds of billions of galaxies in the observable universe. So here is the full ladder. If you dare to climb all the way up, a grain of sand for the Earth, a great ball for the Sun. Shrink that to a grain again, and a boulder for Stephenson 218. And that boulder is one of a handful of giants in a galaxy of hundreds of billions of stars, which is itself one of hundreds of billions of galaxies. At every step, the thing that seemed impossibly large a moment ago becomes a speck against what comes next. This is the true structure of reality, and it is almost impossible to hold in the mind for more than a few seconds at a time before it slips away and becomes just words again. That slipping is not a failure on your part. It is simply what happens when a brain evolved to judge the distance to the next tree tries to grasp the size of a star. There is a deeper mystery lurking behind all of this, one that astronomers are still working to untangle. If red supergiants sit so close to the very limit of what a star can be, then studying them is a way of studying the limit itself. Each one of these giants is a natural experiment, running at scales and pressures and temperatures we could never hope to reproduce anywhere on Earth. Stephenson 218 and its fellow titans are laboratories, testing the laws of physics at the outer edge of what matter can endure. When we watch how they pulse, how they shed their material, how their outer layers behave, we are watching physics operate in a regime we cannot access any other way. And these observations sometimes surprise us. The largest stars have a habit of behaving in ways that do not quite match our models, of being a little too large, or losing mass a little too fast, or pulsing in ways we did not predict. Every one of these surprises is a clue, a hint that our understanding is incomplete, that there is more to learn about how the most massive stars live and die. Consider the strange problem of how these stars manage to grow so large in the first place. We said that radiation pressure sets a ceiling on how massive a star can become, because the light pouring out blows away any extra material. But that raises a puzzle. If radiation pressure is so effective at blowing gas away, how does a very massive star manage to gather all that gas together in the first place during its birth? Should not the growing star blow away its own building material before it ever finishes forming? This is a genuine open question, and astronomers have proposed several ways nature might get around it, involving the way gas falls in along particular channels, or the way material can pile up faster than the light can drive it off. The details are still being worked out, and the very existence of stars as large as Stephenson 218 is part of the evidence that constrains the answer. The giant is not just a spectacle. It is a test case, a data point that our theories of star formation must be able to explain. Then there is the matter of how these stars end and what they leave behind. We said that a star this massive will likely collapse into a black hole when it dies, or perhaps a neutron star if conditions are slightly different. But the exact outcome depends on details we do not fully understand, on precisely how much mass the star has when it dies, on how much it has shed along the way, on the intricate physics of the final collapse. Some very massive stars, it turns out, may not explode in the ordinary way at all. The very largest may collapse directly into black holes with little fanfare, their light simply winking out as the star swallows itself. Others may explode with a violence beyond even ordinary supernovae, in rare and spectacular events driven by exotic physics in their cores. Which path Stephenson 218 will take, we cannot yet say for certain. It sits in a mass range where the outcome is genuinely uncertain, where small differences tip the balance between one dramatic ending and another. In a sense, the star's final chapter is not yet written even in theory, and watching stars like it is how we will learn to read that ending. Let us slow down and really dwell on that final collapse, because it is one of the most extraordinary events in all of nature, and Stephenson 218 is destined to undergo it. For millions of years, the star fights a war against gravity, holding itself up with the energy of fusion. Layer by layer, it works its way through the periodic table, fusing lighter elements into heavier ones, each stage a fresh line of defense against collapse. Hydrogen into helium, helium into carbon and oxygen. Onward through neon and silicon, each stage burning faster and buying less time than the one before. The final stages happen with breathtaking speed. A star that spent millions of years burning hydrogen might burn through its last fuel in a matter of days. The core becomes layered like an onion, each shell fusing a different element, the heaviest and densest material sinking to the center. And at the very heart, iron accumulates. Iron is the ash of stellar fusion, the point where the process gives out. Fusing iron does not release energy. It absorbs it. So when the core becomes iron, the star's furnace does not just weaken, it shuts off entirely, and it does so in the worst possible way. The iron core, growing heavier by the second, finally reaches a critical mass it cannot support, and in a fraction of a second, it collapses. Material that was spread across a region larger than a planet crashes down into a ball just a few kilometers wide. The infall is almost unimaginably fast, a significant fraction of the speed of light. The core reaches a density beyond anything in ordinary experience, denser than an atomic nucleus, and at that point it can compress no further. It rebounds, and a shockwave tears outward through the infalling layers. At the same time, a flood of ghostly particles called neutrinos pours out of the collapsing core, carrying away a staggering amount of energy and helping to drive the explosion. The outer layers of the star, all that vast swollen envelope, are blasted into space at enormous speed. For a few weeks, the dying star blazes with the light of billions of suns, outshining its entire home galaxy. And in the heat and fury of that explosion, elements even heavier than iron are forged, elements that could not be made in the ordinary course of a star's life, created in the extreme conditions of the blast and scattered outward. What remains at the center is the crushed core, and its fate depends on how much mass it holds. If it is below a certain threshold, it settles into a neutron star, an object so dense that a single spoonful of its material would weigh as much as a mountain, spinning perhaps many times a second, a lighthouse of radiation sweeping across space. If it is above that threshold, as it may well be for a star as massive as Stephenson 218, nothing can halt the collapse. The core keeps falling inward, past every limit, until it vanishes behind a horizon from which not even light can return. A black hole is born, a region of space where gravity has won so completely that it has closed itself off from the rest of the universe. The largest star, ending as one of the darkest things that can exist. A giant of light, becoming a well of perfect darkness. Step back again and consider the timescales at play, because they are as staggering as the sizes and just as difficult to feel. Our sun is roughly 4.5 billion years old, and it is not yet halfway through its life. It will keep shining, steady and warm, for another 5 billion years or so before it swells into a red giant and eventually fades. That is the pace of an ordinary star, a slow, patient rhythm measured in billions of years. Now compare that to the life of a giant like Stephenson 218. A star born with tens of times the mass of the sun does not live for billions of years. It lives for only a few million. Its entire existence, from birth to explosive death, might span less time than has passed since our earliest human ancestors first walked upright on the plains of Africa. In cosmic terms, these giants are here and gone in an instant, flaring up brilliantly and vanishing while slower stars barely change at all. There is a strange and moving symmetry in this. The largest, most powerful stars live the shortest lives. They burn with such fury that they consume themselves almost as fast as they form. The dim, modest red dwarfs, the smallest and least impressive stars, will outlive them by a factor of 1,000,000 or more, glowing faintly for trillions of years, long after every giant that ever existed has died and gone dark. The universe seems to hold a quiet rule. The brighter you burn, the sooner you are gone. Stephenson 218 is living proof of it. A star of almost incomprehensible grandeur that is, by cosmic standards, already nearly finished. Its brilliant life, a brief candle flame against the long, slow burning of lesser stars. And when it dies, the cluster it belongs to will lose its greatest member. And in time, new stars will form from the debris, and the cycle will begin again. This is the great rhythm of the galaxy, the endless turning of gas into stars and stars back into gas. Giants are born, live their brief, violent lives, and die, seeding the space around them with the elements of the next generation. From their ashes, new stars form and new planets, and perhaps, on some of those planets, new life, made from the scattered atoms of stars that died long before. We are one link in that chain, standing on a world built from the ashes of ancient giants, looking outward at a living giant that will one day add its own substance to the great recycling of the galaxy. There is something almost comforting in that thought. For all its scale and strangeness, nothing in the cosmos is truly wasted. The death of a star is also a kind of gift, a scattering of the raw material from which new worlds and new possibilities are made. Stephenson 218, in its eventual death, will give back to the galaxy everything it gathered up in its birth, enriched and transformed, ready to become part of something new. Let us return once more to the crowded region of sky where our giant hides, because there is more to say about why this particular corner of the galaxy is so rich in monsters. When you look toward the constellation of the Shield, you are looking along the plane of the Milky Way, into the thick of our galaxy's disk. In that direction lies one of the great structures of our galaxy, a dense concentration of stars and gas that funnels material inward and triggers bursts of star formation. It is a place where the ingredients for building stars are gathered in abundance, and where new stars are being born in great numbers. Clusters like Stephenson 218 form in these active regions, condensing out of giant clouds of gas in batches, dozens or hundreds of stars igniting over a relatively short span of cosmic time. And because the raw material is so plentiful there, some of those newborn stars grow to enormous size, becoming the kind of giants we have been discussing. The region is, in effect, a nursery for titans. If you wanted to find the largest stars in the galaxy, this is where you would look, along these dense inner lanes where star formation runs hot and fast. That is no accident. It is a direct consequence of where the material is and how it behaves. But looking into these rich regions comes at a cost, and that cost is dust. The very clouds that build the stars also hide them. Between us and Stephenson 218 lie vast quantities of interstellar dust, fine grains of solid material scattered through space, and that dust dims and reddens the light passing through it. This is why the star, for all its brilliance, appears so faint from Earth, and why it took infrared observations to reveal it properly. The light we do receive has been filtered, reddened, and weakened by its long passage through the murk. In a way, the galaxy hides its greatest treasures behind veils of its own making, and it takes ingenuity and patient observation to see past them. There is something poetic in the idea that the dust obscuring the star is itself, in part, the product of stars like it. The giants shed material, that material becomes dust, and that dust drifts through the galaxy, dimming the light of other stars, including the giants that made it. The galaxy is woven together in these long loops of cause and effect, stretching across millions of years and thousands of light years. Every part connected to every other. To study one star is, in the end, to study the whole system that produced it. The clouds, the clusters, the dust, the cycles of birth and death that fill the galaxy with light and shadow. Stephenson 2:18 does not stand alone. It is a single, spectacular thread in an enormous tapestry, and pulling on that thread draws the whole pattern into view. There is a question that people often ask when they first hear about a star like this, and it is a natural one. Could such a star ever be a threat to us? Could a giant like Stephenson 2:18, when it finally explodes, harm the Earth? The reassuring answer is no, not from where it sits. Stephenson 2:18 is roughly 19,000 light-years away, an enormous distance, and a supernova at that range would pose no danger to our planet. When it eventually explodes, if it has not already, the light of that explosion will one day reach us, and it may briefly become a bright new point in our sky, visible even in daylight for a time. But the energy will have spread out over that vast distance until it is harmless by the time it arrives, a spectacle rather than a threat. For a supernova to genuinely endanger life on Earth, it would need to be far closer, within a few dozen light-years or so, and there are no stars of that kind lurking that near to us. Our cosmic neighborhood is, thankfully, free of imminent stellar catastrophes, so we can watch these distant giants with wonder rather than fear. They are magnificent, and they are safely remote, playing out their violent dramas at distances that render them beautiful rather than dangerous. If anything, a nearby supernova would be one of the great astronomical events of all time, a chance to study the death of a massive star up close, in unprecedented detail. Astronomers would give a great deal to witness a supernova at a safe but nearer distance, to see the physics of stellar death laid bare. When Stephenson 2:18 does finally die, if its light reaches us within the span of human civilization, it will be an event watched by every telescope on and around the Earth, a once-in-many-generations opportunity to see one of the largest stars ever found end its life. Of course, given the distances and timescales involved, we cannot know when that light will arrive. It could be tomorrow. It could be 100,000 years from now. The star might already have exploded, its final flash still crossing the gulf between us, or it might have millions of years of life left before it goes. There is a strange humility in that uncertainty. We are watching a star whose present state we cannot know, whose fate may already be sealed in ways we will not learn about for ages. All we have is the ancient light, and the story we can read within it. It is worth taking a moment to appreciate just how counterintuitive the physics of these giants really is, because it overturns a lot of what our everyday intuition tells us. In ordinary life, bigger usually means heavier, and heavier usually means denser and more solid. A large rock weighs more than a small one and is just as hard. But stars break these rules completely. The largest stars are not the heaviest, and they are anything but solid. Stephenson 2:18 thousands of times wider than the Sun, contains only around 20 times the Sun's mass. If you think of the Sun as a certain amount of stuff packed into a certain size, then this giant has taken only about 20 times that amount of stuff and spread it across a volume billions of times larger. The result is a star that is, on average, fantastically tenuous. Its outer layers a near vacuum. Its substance stretched so thin that the very concept of a surface becomes blurry. You could fly a spacecraft into the outer envelope of a red supergiant and, at first, barely notice you had entered the star at all. So thin is the gas there. Only as you pressed deeper, toward the core, would the material thicken and the heat and pressure climb toward the extremes that power the star. This is so different from our intuition that it takes real effort to accept. We imagine a star as a solid, blazing ball, like a hotter version of a planet. But a red supergiant is more like a vast, glowing atmosphere with no solid ground beneath it at all. A diffuse cloud held together by gravity, with a dense furnace buried deep at its heart. The image of a hard, definite sphere simply does not apply. And this tenuousness is part of what makes these stars so unstable, so prone to pulsing and shedding their outer layers. The outer envelope is so loosely bound that relatively modest disturbances can send great waves rolling through it, or fling material off into space entirely. The star is enormous, but it is also fragile in a sense. Its vast bulk held together only weakly at the edges, always on the verge of losing pieces of itself to the dark. There is a lesson in this about not trusting our everyday intuitions when we venture into the extremes of the cosmos. The universe operates by the same laws of physics everywhere, but those laws produce results at cosmic scales that would seem impossible to anyone judging by earthly experience. A thing can be unimaginably vast and yet almost weightless for its size. A thing can be a star and yet thinner than air across most of its bulk. The cosmos is full of these surprises, and the largest stars are among the most striking of them. Consider, too, what it would take to actually reach this star, to travel there, because nothing drives home a distance like trying to imagine crossing it. The fastest spacecraft humanity has ever built travels at speeds that feel blistering by earthly standards, tens of kilometers every second, fast enough to cross an ocean in the blink of an eye. And yet, at those speeds, the journey to even the nearest star to our Sun, which is only about 4 light-years away, would take tens of thousands of years. Now consider that Stephenson 218 is not 4 light-years away. It is around 19,000 light-years away, nearly 5,000 times farther than our nearest stellar neighbor. At the speed of our fastest current spacecraft, the journey there would take not thousands but hundreds of millions of years, far longer than our species has existed, longer than there have been mammals on the Earth. Even if we could somehow build a ship that travels at the speed of light itself, the fastest anything can possibly go, the trip would still take 19,000 years in each direction. You would leave the Earth, and by the time you arrived, all of recorded human history would have unfolded twice over back home in your absence. This is why we will almost certainly never visit stars like this, not in any time frame that means anything to human lives. They are not destinations. They are objects of study, known to us only through the light they send us, light that itself has been traveling for 19,000 years to arrive. And yet, there is something wonderful in the fact that we can know them so well without ever going near them. We have never touched this star, never sent a probe within thousands of light years of it, never will. And still, from our small planet, using nothing but the faint light that reaches us and the power of careful reasoning, we have measured its size, its temperature, its brightness, its distance, and traced out the whole arc of its life and death. That is one of the quiet triumphs of the human mind, that we can stand on the surface of one small world and comprehend objects so vast and so remote that we could never hope to reach them. We are physically tiny and cosmically confined, bound to our little planet, and yet in understanding, in reach of thought, we have touched the largest stars in the galaxy. There is a kind of freedom in that, a way in which the mind escapes the limits of the body and travels distances the body never could. When you understand Stephenson 2:18, you have, in a real sense, been there, further than any ship will ever carry you. Let us think for a while about the surface of this star, or what passes for a surface, because it is one of the most alien environments imaginable. On our Sun, the surface is a churning sea of hot gas, marked by darker patches where magnetic fields suppress the flow of heat, and by brilliant flares that leap out into space. It is violent and dynamic, but on a scale we can at least begin to picture. Now magnify that violence and expand it across a surface thousands of times larger, and cool it to a deep, sullen red, and you begin to approach what the outer regions of Stephenson 2:18 might be like. The gas there is organized into vast convection cells, great columns of rising and sinking material, each one carrying heat up from the depths and radiating it away into space before sinking back down. On the Sun, these convection cells are relatively small, covering the surface in a fine granular pattern. On a red supergiant, the cells are monstrous, each one potentially larger than the entire orbit of the Earth around the Sun. A handful of these enormous cells might cover the whole visible face of the star at any given time, giving its surface a blotchy, irregular, ever-changing appearance, with great bright regions where hot gas wells up and darker regions where cooler gas descends. The star does not have a fixed, smooth face. It has a slowly boiling, shifting patchwork, evolving over months and years, never the same twice. And rising above even this churning surface, the star is wrapped in an extended atmosphere of gas that has been lifted off it, a tenuous halo reaching far out into space, gradually merging with the material the star has shed over its lifetime. There is no clean line where the star stops and space begins. There is only a gradual thinning, the dense furnace at the center giving way to the convecting layers, then to the extended atmosphere, then to the outflowing wind, then to the surrounding shroud of expelled material, and finally to the true emptiness of interstellar space. The star bleeds into its surroundings, and its surroundings are, in a sense, still part of the star. To ask exactly how big it is, then, is to ask a question with a fuzzy answer, because the star does not have a sharp edge to measure. When astronomers give a radius, they are choosing a particular definition, a particular layer to call the surface, and measuring to there. Different definitions give slightly different numbers, which is another source of the uncertainty that surrounds these giants. The star itself does not care about our definitions. It simply exists, vast and diffuse and boiling, trailing off into the dark, indifferent to our attempts to draw a neat circle around it and label it with a number. It is fascinating to consider how the study of stars like this connects to some of the biggest questions in all of science. The most massive stars, the ones that end their lives in supernovae and leave behind neutron stars and black holes, are the forges where most of the heavy elements in the universe are made. Without them, the cosmos would be a far simpler and far emptier place, made almost entirely of the two lightest elements, hydrogen and helium, with little else. There would be no carbon for life, no oxygen for water, no iron for planets and blood, no silicon for rock. All of that richness, all of the chemical variety that makes complex worlds and living things possible, was manufactured inside massive stars and scattered by their deaths. Stephenson 218 and its kind are, in a very real sense, the source of the material universe as we experience it. When we study these giants, we are studying our own origins, tracing the chain of events that led from a simple early universe of hydrogen and helium to the complex, element-rich cosmos we inhabit today. Every atom heavier than helium in your body was made inside a star, and the largest, most massive stars did more than their share of that making. There is a beautiful continuity here, a thread that runs from the largest stars in the galaxy all the way down to the smallest details of your own body. The calcium in your teeth, the iron carrying oxygen through your blood, the phosphorus in your bones, the sodium and potassium that let your nerves fire and your thoughts form. All of it was cooked in stars and scattered across space long before the Earth existed. You are, quite literally, made of stardust, and some of that stardust came from giants like the one we have been exploring. When you look up at the night sky and see the scattered stars, you are looking at the same kind of furnaces that made you, still burning, still forging the elements of future worlds. And somewhere out there, hidden behind dust, one of the largest of them all is burning still, or perhaps already gone, its final light still crossing the void toward us. To understand Stephenson 218 is to understand a little more about where everything came from, including ourselves. That is perhaps the deepest reason these giants matter, beyond the sheer spectacle of their size. They are not just record holders, not just curiosities to marvel at. They are engines of creation, building the raw material of the universe, and their story is, ultimately, our story too. Let us go back, one more time, to the simple act of measurement, and to just how remarkable it is that we can measure the angular size of a star at all. From Earth, even the largest, nearest stars appear as nothing more than points of light. They are so far away that no ordinary telescope can resolve them into disks. They remain pinpricks, no matter how much you magnify them. This is a problem, because to measure a star's true size directly, it would help enormously to be able to see it as a disk rather than a point. For most stars, including Stephenson 218, we cannot do this directly, and so we rely on the indirect chain of reasoning we described earlier, using brightness, temperature, and distance. But for a handful of the nearest and largest stars, using extraordinarily clever techniques that combine the light from multiple telescopes, astronomers have actually managed to measure their disks directly, to resolve them as more than points. These measurements are astonishingly difficult, pushing the limits of what our instruments can do, but they have confirmed the basic picture. The largest stars really are as enormous as the indirect methods suggest. When you can measure a star both ways, directly and indirectly, and the two methods agree, your confidence in the whole approach grows. This is how science builds trust in its conclusions, by attacking the same problem from independent directions and seeing whether the answers line up. For a star as distant as Stephenson 218, direct disk measurement is beyond our current reach, but the methods used to measure it have been validated on nearer giants, and that gives us reason to trust them. As our instruments continue to improve, the day may come when we can resolve even distant giants like this one and measure their sizes directly, settling the uncertainties that currently surround them. The history of astronomy is, in large part, a history of steadily improving our ability to measure things once thought unmeasurable. Distances to stars, once impossible, became routine. The compositions of stars, once thought forever unknowable, were read from their light. The sizes of stars, once mere guesses, became precise figures. Each generation of astronomers has pushed the boundary of what can be known a little further out, and there is every reason to expect that trend to continue. The numbers we quote for Stephenson 218 today are the best we can currently do, and they are already remarkable. Tomorrow's astronomers, with better tools, will do better still, and the picture of this giant will grow sharper and more certain. That is the nature of the enterprise, an endless refinement, an ever closer approach to the truth, never quite complete, always improving. There is a philosophical thread worth pulling on here, about what it means for something to be the largest. When we crown Stephenson 218 as the largest star ever discovered, we should be careful about what that claim actually means. It does not mean it is the largest star that exists. It means it is the largest we have found and measured so far. The galaxy contains hundreds of billions of stars, and we have carefully measured only a tiny fraction of them. Vast regions of the galaxy are hidden from us behind dust, or simply too far and too faint to study in detail. There could easily be a star out there, even larger than Stephenson 218, hidden in some unexplored corner of the galaxy, waiting to be found. In fact, given how little of the galaxy we have thoroughly surveyed, it would be surprising if there were not. So the title of largest known star is provisional, a snapshot of our current knowledge rather than a final verdict on the universe. It has changed hands before, and it will change hands again, as new giants are discovered and old measurements are refined. This is not a flaw in the science. It is a sign of how young and incomplete our exploration of the galaxy still is. We are like early mapmakers who have charted only the coastline of a vast continent, marking the largest mountain we have seen so far, while knowing full well that greater peaks may lie in the unmapped interior. Every new survey, every new telescope, every advance in our ability to see through the dust pushes the boundary of the known a little further, and occasionally turns up a new record holder. There is something thrilling in that ongoing uncertainty. It means the story is not finished. It means that somewhere out there, the true largest star may still be waiting, unseen, and that some future astronomer may one day find it and rewrite the record books. The universe is still keeping secrets, still holding some of its grandest objects just out of view, and the search to find them goes on. Stephenson 218 is the current champion, and a worthy one, a genuine titan pressed against the limits of what a star can be. But it wears its crown lightly, knowing that the search continues and that the cosmos may yet reveal something even greater. That, perhaps, is the most exciting thing of all. Not that we have found the largest star, but that we are still looking, still discovering, still capable of being astonished by what the universe contains. Let us dwell for a moment on the strange relationship between size and permanence, because it runs contrary to what we might expect. We often associate great size with strength and endurance. The largest mountains seem the most permanent features of a landscape. The largest trees seem the most enduring living things. We imagine that to be big is to be lasting. But among the stars, the opposite is true. The largest stars are the most fleeting, the most short-lived, the most fragile in their own way. Stephenson 218, for all its overwhelming size, is a creature of the moment, cosmically speaking, a brief and brilliant flame that will gutter out in a geological instant. Its very size is a symptom of its impending death, a sign that it has already burned through the youthful phase of its life and swollen into its final, unstable form. The largest a star ever gets is precisely when it is closest to the end. There is a strange melancholy in that, and also a strange beauty. The giant is at its most magnificent at the very moment it is most doomed. Its grandeur and its mortality are bound together, inseparable, two faces of the same fact. To grow that large is to be dying. To reach that size is to be nearly finished. The star cannot be both enormous and enduring. It can only be enormous and brief, a spectacular final act before the curtain falls. Compare that to the smallest, dimmest stars, the red dwarfs, which will outlast every giant by unimaginable spans of time. Those humble stars, barely worth a second glance, will still be quietly shining trillions of years from now, long after every giant that has ever existed has died, long after the era of bright galaxies has faded, long into the deep future of the universe. The meek stars inherit the cosmos. The giants blaze and vanish. There is a lesson in that about the nature of magnificence, though it is not a comfortable one. The most spectacular things are often the most transient. The brightest flames burn out the fastest. And to shine with the greatest brilliance is, in some sense, to spend oneself most quickly. Stephenson 218 embodies this truth on a cosmic scale, a star of almost unimaginable grandeur that is, for exactly that reason, already near its end. When we look at it, we are looking at magnificence and mortality fused into a single object, the largest and among the most doomed of stars, burning brilliantly in the brief moment before the dark. Now imagine trying to build a scale model of all this, something you could hold in your hands to bring the numbers down to a human size. Suppose you shrank the sun down to the size of a single small marble, about a centimeter across. At that scale, the Earth would be a speck of dust, tinier than a grain of sand, orbiting about a meter away from the marble. The whole inner solar system would fit within a few meters. Jupiter would be a small bead several meters out, and Saturn a smaller one a bit farther still. Now, at this same scale, where the sun is a marble, a centimeter across, how large would Stephenson 218 be? It would be a sphere roughly 40 meters across. Picture a marble sitting on the ground, and then picture a glowing sphere the size of a large building rising up beside it. That is the ratio between our sun and this star, made visible. And that great sphere, roughly 40 meters across in our model, would have its surface reaching out to about where Saturn's tiny bead orbits the marble, some 10 meters from the center. The whole planetary system that we call home would be buried inside it. This is the kind of exercise that finally lets the numbers land, even if only for a moment. When the sun is a marble and the star is a building, and the Earth is an invisible speck of dust, you begin to feel, in your gut rather than just your head, what these scales actually mean. And then, if you want to push further, remember that this building-sized sphere is one of the largest objects the galaxy contains. And the galaxy is so vast that if you shrank the whole thing down until the distance between the sun and the nearest star was the length of your arm, the galaxy would still be wider than a continent. At every scale, the previous scale shrinks to nothing. The Earth vanishes against the sun vanishes against the star vanishes against the galaxy vanishes against the universe. It is scales within scales, each one swallowing the last, stretching upward beyond any hope of intuition. And we, the ones doing all this measuring and imagining, are smaller than the speck of dust that stood for the Earth in our model. We are motes upon a mote, and yet we have looked out across all of it and begun to understand. That contrast between our physical smallness and the reach of our understanding is perhaps the most astonishing thing in this whole story. The largest star ever found is a wonder, but so is the tiny, curious mind that managed to find it and measure it and comprehend its size. From across 19,000 light-years of empty space, there is one more aspect of these giants that deserves attention, and it concerns their color, that deep, brooding red that gives them their name. Why are the largest stars red, rather than the brilliant blue, white, or yellow of hotter stars? The answer lies in the relationship between a star's surface temperature and the color of light it gives off. Hotter surfaces glow with bluer light, and cooler surfaces glow with redder light. The same way a piece of metal heated in a fire glows first dull red, then orange, then yellow, then white as it gets hotter. The surface of our sun, at around 5,500 degrees, glows with a light we perceive as roughly white or yellowish. The surface of a hot, young, massive star can reach tens of thousands of degrees, and it glows a fierce blue-white. But the surface of a red supergiant like Stephenson 218 is relatively cool, only around 3,000 degrees, and so it glows with a deep red light. This coolness is a direct consequence of the star's enormous size. When a star swells to supergiant proportions, its surface is spread across such a vast area that the heat rising from within is diluted, spread thin over an enormous surface. And so the surface itself is cooler than it would be on a smaller star. The star is not cool overall, of course. Its core is hotter than ever, burning fiercely. But the surface, the outermost layer we see, is cool and red precisely because it is so far from the core and so spread out. So the red color is a kind of signature of great size, a sign that the star has bloated outward and cooled at its surface. When you see a deep red giant in the sky, you are seeing a star that has entered the swollen final phase of its life. The reddest, coolest, largest stars are the ones nearest the end. There is a whole language written in the colors of the stars, if you know how to read it. Blue means hot, young, and often massive. Red can mean cool and small, in the case of the humble red dwarfs, or cool and enormous, in the case of the red supergiants, and astronomers can tell the difference by measuring the star's brightness. A faint red star is a small, cool dwarf. A brilliant red star, pouring out the light of hundreds of thousands of suns, is a supergiant in its death throes. Stephenson 218 is the latter, a red giant of the most extreme kind. Its deep crimson glow, a beacon marking one of the largest and most doomed stars in the galaxy. The color that we might casually call beautiful is, read correctly, the color of an ending. It is worth reflecting on how recent all of this knowledge really is. For the vast majority of human existence, nobody had any idea that stars came in such wildly different sizes. The idea that one star could be thousands of times larger than another, that some could swallow whole solar systems, while others were barely larger than a planet, would have been utterly beyond the reach of anyone living even a few centuries ago. The tools needed to discover these things simply did not exist. The understanding of what stars are, how they work, what powers them, and how they live and die is largely a product of the last century or so. A mere eye blink in the long story of our species. Within living memory, our picture of the stars has been transformed from a scattering of mysterious lights into a detailed understanding of stellar birth, life, and death, of the forces that shape stars and the limits that constrain them. Stephenson 218 itself was recognized as an exceptional object only recently. Its true size worked out with modern instruments and modern understanding. We are, in a real sense, the first generations of humans ever to know that a star like this exists. Think about that. For hundreds of thousands of years, our ancestors looked up at the same sky, and the giant was there the whole time, hidden behind its veil of dust, unknown and unimagined. And only now, in our own moment, has it been found and understood. We happen to be alive at the particular point in history when it became possible to know these things, when the tools and the theories finally came together to reveal the true nature of the largest stars. That is a remarkable privilege, and one that is easy to take for granted. We inherit an understanding of the cosmos that no previous generation possessed, built up through centuries of patient observation and reasoning. And we get to look out at the universe, knowing things that would have seemed like magic or madness to our ancestors. The largest star ever discovered is part of that inheritance, a piece of knowledge that belongs to our era, hard-won and freely available to anyone curious enough to seek it out. And the story is far from over. The tools keep improving. The surveys keep expanding. The understanding keeps deepening. The generation after ours will know things about these giants that we cannot yet imagine. We'll refine the numbers, resolve the uncertainties, and perhaps find new record holders lurking in the unexplored depths of the galaxy. We stand at one point on a long journey of discovery, looking back at how far we have come and forward at how much remains to be found. And the giant burns on, indifferent to our knowing, exactly as it did before we ever learned its name. Let us take a moment to imagine the long future of this star, playing out the story to its conclusion, even though we will never live to see it. Right now, Stephenson 218 hangs in the sky as a swollen red supergiant, pulsing and shedding its outer layers, its core working through the final stages of fusion. For however long it has left, whether that is thousands of years or millions, it will continue in this state, growing ever more unstable, throwing off ever more material, wrapping itself ever more thickly in shells of expelled gas. Then, when the core finally fills with iron and can hold out no longer, the collapse will come, and the star will die in a burst of light brighter than a galaxy. The outer layers will be flung outward at tremendous speed, an expanding cloud of debris racing away from the collapsed core, seeded with the elements the star forged over its lifetime. This cloud will spread out across space, thinning and cooling over thousands and then millions of years, mixing with the surrounding gas of the galaxy. And at the center, if the collapse produced a black hole, there will be a small, dark, invisible object, a region of space sealed off from the rest of the universe, all that remains of a star that once could have swallowed our entire inner solar system. The vast red giant, thousands of times wider than the sun, will have become a point of perfect darkness, only a few kilometers across, denser than anything else in nature. From the largest to the smallest, from the brightest to the darkest, in a single collapse. The expelled material, meanwhile, will drift onward, enriching the galaxy, becoming part of the raw material for future stars and planets. Perhaps, in some distant age, a new star will condense from a cloud that includes the scattered atoms of Stephenson 218, and around that new star, planets may form, built in part from the substance of the ancient giant. And who knows what might arise on those worlds, made from the recycled material of a star that died long before. This is the great cycle of the galaxy, playing out over billions of years, the endless turning of matter from stars into space and back into stars. Stephenson 218 is one turn of that wheel, one giant living its brief life and giving itself back to the galaxy in death, its substance destined to become part of something new. We will not see it happen. The timescales are far too long, and the distances far too great. But we can trace the story in our minds, from the star's fiery birth to its swollen present to its violent future, and in doing so, we can understand our own place in the same great cycle. We too are made of the ashes of ancient giants. We too are one turn of the wheel. And when we look at Stephenson 218, we are, in a way, looking at both our origin and our kinship, at the kind of object that made the atoms in our bodies, still doing its ancient work far across the galaxy. There is a common misconception worth clearing up, one that trips up many people when they first encounter these giants. People sometimes assume that the largest star must also be the brightest star in our sky, or the most famous, or the one you can easily point to on a clear night. None of this is true. Stephenson 218, for all its staggering size, is invisible to the naked eye. You could stand under a perfectly dark sky, look directly at the patch of the heavens where it lies, and see nothing at all where the giant hides. It is far too distant and far too dimmed by dust to be seen without powerful instruments. The brightest stars in our night sky are not the largest stars in the galaxy. They are simply the ones that happen to be relatively near to us, or that happen to shine in wavelengths our eyes can catch through the intervening space. Some of the most brilliant points in our sky are stars only modestly larger than the Sun, close enough to appear bright. Meanwhile, the true giants, the record-breaking supergiants, are so distant and so shrouded that they never register as more than faint smudges, if they can be seen at all. There is a lesson in this about the difference between apparent brightness and true grandeur. The most impressive objects are not always the ones that catch the eye. The largest star ever found is not a dazzling beacon in our sky. It is a hidden monster, revealed only to those who know how to look, using tools that see beyond the range of human vision. Its grandeur is real, but it is not obvious. You have to seek it out, understand it, and work to appreciate it, and that effort is part of what makes it so rewarding to know about. The universe does not hand its greatest wonders to the casual glance. It reserves them for the curious, the patient, the ones willing to look closely and think hard. Stephenson 218 is a giant that hides in plain sight, its true nature invisible to anyone who does not go looking for it. A reminder that the most extraordinary things are often the ones we cannot see without effort. And once you know it is there, once you understand what that faint smudge of infrared light really is, the sky is never quite the same again. You look toward the constellation of the Shield, and even though you cannot see the giant, you know it is there. Burning across 19,000 light-years of space, the largest star ever found, hidden behind the dust, waiting in the dark. Let us pause on the sheer improbability of a star like this existing at all, because when you consider everything that has to go right for such an object to form, it becomes even more remarkable. A star of this size requires an enormous amount of raw material gathered together in one place, far more than goes into an ordinary star. It requires that material to collapse and form a single star rather than fragmenting into many smaller ones, which is what usually happens when a large cloud collapses. It requires the star to survive its own violent birth, when the intense radiation of a newborn massive star tends to blow away the very gas it is trying to gather. It requires the star to reach the end of its main life and swell into a supergiant, ballooning outward to its maximum extent, and to do so at just the moment we happen to be looking. Every one of these steps is a narrow window, a set of conditions that must be met, and the fact that they all came together to produce Stephenson 218 is a kind of cosmic good fortune. Massive stars are rare to begin with, making up only a tiny fraction of all the stars in the galaxy. The most massive of those are rarer still. And catching one in the brief supergiant phase, at its maximum size, is rarer yet again. So when we look at Stephenson 218, we are looking at the product of a whole chain of unlikely events, a genuine rarity, one of just a handful of true giants in a galaxy of hundreds of billions of stars. It is the cosmic equivalent of finding the single tallest tree in a vast forest, at the exact moment of its greatest height, just before it falls. That rarity is part of what makes it precious, scientifically and otherwise. Each of these giants is a rare specimen, a chance to study the extreme end of what stars can do. And there are so few of them within reach that every one is valuable. Astronomers treasure these objects, study them intensely, and squeeze every drop of information they can from the faint light they send us, because such objects do not come along often, and because they teach us things we can learn nowhere else. Stephenson 218 is not just a record holder. It is a rare and precious window into the most extreme physics of stars, a natural experiment of a kind we could never construct ourselves, running quietly across the galaxy for us to observe. And in observing it, We learn not just about this one star, but about the limits of stars in general, about how big they can get, how they live at the extreme, and how they die. One rare giant, teaching us the rules that govern them all. Before we bring this journey to a close, let us gather together everything we have learned and hold it all in view at once, so the full picture can settle into place. We began with our own world, a ball of rock 12,700 kilometers across, and it felt large. We set it beside our sun, and it shrank to a speck, one of more than 1,000,000 that could fit inside our star. We learned that our sun, mighty as it is classified as a modest yellow dwarf, an ordinary star among the hundreds of billions that fill our galaxy. We saw that stars come in a vast range of sizes, shaped by how much material they were born with, and that the biggest, brightest stars burn hardest and die soonest. We traveled across 19,000 light-years, into a crowded region of the galaxy behind veils of dust, to a cluster called Stephenson 218, and there we found a red supergiant so vast that it defies comprehension. We learned that its radius is around 2,150 times that of our Sun, that light itself would need nearly 3 hours to cross it, and that if it took the Sun's place, it would swallow the inner planets and reach out to about the orbit of Saturn. We discovered the strange truth that this enormous star holds only around 20 times the Sun's mass, spread so thin across its vast volume that it is, on average, more tenuous than air. We followed its life story, from a brilliant blue-white birth, through its furious burning of fuel, to its swollen red supergiant present, and onward to its violent future, when it will collapse and explode, likely leaving behind a black hole. We saw how the elements it forges will be scattered across the galaxy, becoming the raw material of new stars and worlds, just as the giants of the past made the very atoms in our bodies. We came to understand that its title as the largest star ever discovered is provisional, a snapshot of our current knowledge, and that greater giants may yet be found in the unexplored depths of the galaxy. And through all of it, we kept returning to the same astonishing fact that we, tiny creatures on a small planet, have managed to find and measure and understand an object so vast and so remote that we could never hope to reach it. That is the true wonder of this story. Not just the size of the star, staggering as it is, but the reach of the mind that comprehended it. We have looked across 19,000 light-years of empty space, past clouds of obscuring dust, and worked out the size, the temperature, the brightness, the life, and the death of a star we will never touch. We have held a giant in our understanding and made it, in a small way, our own. It is worth considering, too, how a star like this fits into the wider family of extreme objects that fill the cosmos, because Stephenson 218 is a champion of one particular kind, but the universe holds records of many different sorts. There are stars that are the most massive, packing the greatest amount of material into a relatively compact ball, dense and heavy, rather than sprawling and wide. There are stars that are the hottest, blazing at surface temperatures of tens of thousands of degrees, pouring out most of their energy as searing ultraviolet light. There are stars that are the most luminous, releasing torrents of energy that dwarf the output of our sun by millions of times. And there are stars, like Stephenson 218, that hold the record for sheer physical size, for the greatest distance from center to edge. These records do not all belong to the same star, because the qualities that make a star large are not the same as the qualities that make it massive or hot or luminous. A star can be the widest without being the heaviest, exactly as we have seen. A star can be the hottest without being the largest. The universe distributes its extremes across many different objects, each one a champion in its own category. And part of the fascination of studying the stars is mapping out these various records and understanding what produces each one. Stephenson 218 holds the crown for physical size, or comes very close to it, and that is a distinct and remarkable achievement, separate from all the other ways a star can be extreme. To be the widest star is to have swollen to the very edge of what the balance of forces inside a star will allow, to have ballooned outward to the maximum extent before the star would simply come apart. It is a record of expansion, of reaching outward, rather than of raw power or heat or mass. And there is something fitting about that, because the story of this star has been, above all, a story of size, of scale, of the sheer dizzying vastness that a single object can attain. Among all the ways to be extraordinary, Stephenson 218 has chosen bigness, and it has pursued that quality to the very limit that nature permits. It is worth remembering, as well, that our understanding of all these records is constantly shifting. New surveys turn up new candidates. Old measurements are refined and sometimes overturned. The star that holds a given record today may yield it tomorrow to a newly discovered rival, or to a remeasurement of an old one. This is not a sign of confusion, but of progress, the natural churn of a science that is still actively exploring its subject, still finding new objects, and sharpening its knowledge of old ones. The list of largest known stars is a living document, revised as our reach extends and our instruments improve, and Stephenson 218 sits near its top for now. A worthy champion in a contest that never quite ends. There is a final thought worth sitting with, one that ties the whole story back to you, standing or sitting, wherever you are as you take this in. You are made of atoms that were forged inside stars, many of them inside massive stars, like the one we have been exploring. The iron carrying oxygen through your blood right now was made in the heart of a dying giant and scattered across space in an explosion long before the Earth existed. The calcium giving structure to your bones, the carbon forming the backbone of every molecule in your body, the oxygen you breathe, all of it was cooked in stellar furnaces and flung out into the galaxy when those stars died. The material that became our sun, our planet, and everything on it, including you, was gathered from clouds of gas enriched by generations of stars that lived and died before us. So when you look at Stephenson 218, you are not looking at something alien and separate from yourself. You are looking at the same kind of object that made you, still burning, still forging the elements from which future worlds and future life will be built. There is a deep kinship there, across 19,000 light-years and across billions of years, linking the largest star ever found to the atoms in your own hand. Every heartbeat depends on iron that was born in stellar fire. Every thought you have flickers through nerves that run on elements cooked in the cores of massive stars. Every breath draws in oxygen that was manufactured in stellar furnaces and scattered across the galaxy long before our sun ever ignited. You are not merely an observer of the cosmos, watching it from the outside. You are a piece of it, assembled from its own material, temporarily arranged into a form that can look back and understand where it came from. The atoms that make you were forged in giants, drifted through space for ages, gathered into a cloud, condensed into a planet, and eventually organized themselves into a living, thinking being capable of gazing at other giants across the void. The giant and you are made of the same stuff, bound by the same physics, part of the same great story of matter organizing itself, burning, dying, and being reborn. And in you, that matter has done something extraordinary. It has arranged itself into a form that can look outward, comprehend its own origins, and understand the giants that made it. The universe, through you, has become able to contemplate itself, to measure its largest stars, and to marvel at their grandeur. That may be the most remarkable thing of all in this entire story. Not the size of the star, but the fact that a small arrangement of stellar ash, standing on a tiny planet, can look up and understand it. We began this journey wondering how big something can get before the universe says no more. We have found our answer, or at least the best answer we currently have, in the form of a red supergiant so vast it could swallow the inner solar system whole, pressed against the very limit of what a star can be. But perhaps the deeper answer is that there is no true limit to how far understanding can reach. The star is bounded. Physics draws a line and says this far and no farther. But the mind that comprehends the star is not bounded in the same way. It can reach across any distance, grasp any scale, and hold the largest objects in the universe within a single thought. The next time you find yourself under a dark sky, look toward the faint constellation of the Shield, low along the band of the Milky Way. You will not see the giant. It is far too distant and too hidden for that. But you will know it is there, burning across the vast gulf of space, the largest star ever discovered, a monster of glowing gas, thousands of times wider than our sun, wrapped in dust, pulsing in the dark, living out the final chapter of its brief and brilliant life. And you will know that its light and its story and its very atoms are connected to you across all that distance and all that time. We are the universe looking at itself, and in the largest of stars, we have caught a glimpse of just how vast, how strange, and how magnificent that self truly is. Thank you for taking this journey to the largest star ever discovered. If it filled you with wonder, be sure to like this video and subscribe for more journeys into the cosmos. And remember, you are made of stars.